When you picture a massive ship carrying dry bulk cargo, you probably imagine one of the simplest forms of global transport, right?
Yeah, just a big box, basically.
Exactly. Fill it up, send it across the ocean. But the reality of this massive vital industry is actually, well, far more complex.
Oh, absolutely.
It's riddled with hidden intricacies and some surprising dangers lurking just beneath the surface.
Mm-hmm.
That's exactly what we're diving into today.
Mm,
The critical, often unseen world of dry bulk cargo shipping.
right.
We've pulled from uh, a stack of industry bulletins, safety guides, articles from marine transport publications, trying to give you a really comprehensive look
Yeah, get the full picture.
at the challenges involved. I mean, everything from the cargo types themselves to ship maintenance and the sort of intricate dance of handling operations.
And our mission for you, really, is to fundamentally transform your understanding of what truly goes into getting, raw materials and commodities from point A to point B across the globe.
Right. Beyond the big box idea.
Exactly. We want to highlight the precise details, the diligent efforts required to prevent catastrophic failures and massive financial losses.
We're aiming for those genuine aha moments,
Yeah.
the ones that will leave you truly well-informed about a sector that's anything but simple.
A sector that underpins so much.
Okay, let's unpack this then.
Mm.
We envision a bulk carrier as this, simple cavernous space for cargo.
The basic image, yeah.
But the reality of their holds, it tells a much more intricate story, doesn't it?
Mm-hmm.
Starting with their very design.
It really does. What's fascinating here is how the whole structure itself can inherently contribute to problems.
How so?
Well, conventional bulk carriers, for instance, they often have this box construction, but with large internal frames, big metal ribs inside.
Okay.
And these frames, they can be physically impossible to fully access for cleaning.
Ah, I see. You just can't reach everywhere.
Exactly. Which means corrosion, scale, residues from previous cargoes, they just build up
Got it.
easily, leading to contamination of the next load.
That makes perfect sense. You can't clean what you can't reach. But what about the ships specifically designed for easier cleaning? I've heard of those.
Right. You're probably thinking of box holds. You see them a lot in smaller coastal vessels.
Yeah,
They feature smooth steel sides, which definitely helps.
but I guess there's always a catch.
Well, yeah, even these aren't without their unique issues. They often have adjacent ballast tanks right next to the hold,
Okay.
and these tanks can be prone to leakage, often from grab damage during loading or unloading.
So the equipment damages the tank wall from inside the hold.
Precisely. Even seemingly minor operational issues can cause significant structural harm over time.
You mentioned grab damage. Just how much can discharge equipment really, tear up a ship?
A surprising amount, actually. The ship's internal structure, things
Mhm.
like ladder rails, pipe fittings, access ways, they can be severely damaged.
Right.
And this isn't just cosmetic. Any such damage, it really must be continuously repaired.
Because otherwise,
Otherwise, it can lead directly to cargo contamination, which we mentioned, but also claims from shoreside machinery, pieces of the ship falling off and damaging port equipment.
wow, okay. So it's a constant battle against wear and tear in a really harsh environment.
It really is. An environment designed for heavy-duty work, but still vulnerable.
Let's switch gears slightly. Water seems like such a basic element, right? Just H2O.
You think so?
But in dry bulk shipping, it sounds like it's a major antagonist.
Oh.
Leads to some incredibly costly and dramatic incidents.
Oh, absolutely. If we connect this to the bigger picture, water ingress, water getting where it shouldn't is a pervasive, almost insidious threat.
Got an example?
Sure. Consider a case we saw. A ship loaded with aluminum hydroxide in Australia heading for the USA.
Okay.
A staggering 500 tons of cargo valued around, $150,000, all damaged by seawater ballast.
500 tons. How big was the leak?
That's the kicker. It came from a relatively small hole, maybe 100 millimeter by 20 millimeter, like 4 inches by less than an inch.
No way.
Yeah. Likely caused by stevedore grab damage in the discharge port. Just a small puncture between the hold and a ballast tank.
That is a huge loss from such a tiny hole. It really underscores the absolute necessity of vigilance, especially with water-sensitive cargoes.
It really does. And it's not always obvious damage. Take another dramatic case. This involved a cement cargo, Taiwan to the USA.
Cement. Sounds like it doesn't mix well with water.
Exactly. The master took on additional ballast during a ballast water exchange at sea, which is routine, but water seeped into a hold through a hidden corrosion hole in the trunking.
Trunking. Could you quickly explain that for us? What is that exactly?
Absolutely. Think of trunking as like a hidden channel or a conduit, a passageway connecting different tanks or compartments within the ship's structure.
Okay.
In this case, it was connecting the double bottom, the very bottom space of the ship, and the upper wing tanks, which are located higher up on the sides, kind of under the deck edge.
Got it. A hidden connection.
Right. A seemingly minor passage, but one that proved disastrous because of this hidden corrosion hole. And critically, the master, unfortunately, didn't question why the upper wing tank suddenly became slack, meaning the water level dropped unexpectedly.
Ah, a missed warning sign.
A key sign of a leak, yeah. The outcome. Over 1,000 tons of cement mixed with seawater, creating what the industry grimly calls a cement box.
Cement box. That's a vivid and frankly terrifying image. How do you even fix something like that? It sounds like solid rock.
Pretty much. It took over 6 weeks to dig out, chiseling, breaking, a huge job.
6 weeks. The cost must have been enormous.
More than $2 million, and that's before you even account for the off-hire costs of the ship being out of service all that time.
Unbelievable.
And what this incident lays bare isn't just the physical damage, it's a stark illustration of how a simple oversight, maybe a master not questioning a slack tank reading, can cascade into a multi-million-dollar catastrophe.
It shows that even routine operations demand just extraordinary vigilance.
Absolutely. No room for complacency.
So what does this all mean for preventing water damage? What are the key takeaways here?
Well, it means constant, unwavering vigilance. That's the main thing.
On deck, you mean?
Yeah, the cargo watch on deck needs to be actively monitoring how the stevedores are handling the grabs, keeping a close eye on ballast operations, and immediately identifying potential leak points after any suspected grab damage.
And checking the tanks.
Definitely. A rigorous sounding regime in port meticulously checking tank levels with sounding tapes or sensors is also absolutely critical, catching those anomalies early.
But the challenges aren't always so obvious, like a direct leak. Even the atmosphere inside the hold can turn on you, right? What about the air itself?
Right, you're touching on condensation. We talk about ship sweat and cargo sweat.
Sweat?
Yeah, basically condensation forming on the cold steelwork of the ship. That's ship sweat. Or on the surface of the cargo itself. That's cargo sweat.
And that causes problems.
Big problems. It can lead to mold growth, accelerated decomposition. It's all about managing the temperature and humidity balance between the cargo, the air in the hold, and the outside environment.
So ventilation is key.
Correct. Ventilation is crucial. But doing it wrong, or say loading cold cargo into a warm, humid environment, can lead to significant condensation damage that looks very much like water ingress, but it's actually an atmospheric issue.
Fascinating. This whole discussion around water.
Yeah.
It also leads us to something incredibly important for safety. Liquefaction. That just sounds bad.
It is. It's very real and, frankly, terrifying.
Yeah.
Liquefaction and a related issue, dynamic separation, they occur when certain bulk cargoes, particularly mineral concentrates like iron or fines or nickel ore, have too much moisture.
Too wet, basically.
Too wet, and also a specific particle size distribution. It needs to be fine enough. Under the vibration and movement of the ship at sea, the cargo compacts, it settles, and the water squeezes out, turning the top layer or even the whole mass into something fluid-like.
So a solid cargo literally turns into a liquid and starts sloshing around, like a giant mud puddle in the hold.
Exactly like that. And this liquid-like state poses severe risks, uncontrollable cargo shifting.
Which could make the ship list.
Violently, causing the ship to list dangerously, potentially capsize, or even suffer structural damage from the shifting weight and the free surface effect of this fluid-like cargo.
Resurface effect.
Yeah, imagine a half-filled water bottle in a moving car, how the sloshing amplifies the movement and instability. Same principle, but on a massive scale inside a ship's hold. It severely reduces the ship's stability.
Okay, that is genuinely scary.
Which is why, for what are called Group A cargoes, those known to be prone to liquefaction, the moisture content, the MC, must always be below its transportable moisture limit, or TML.
TML, transportable moisture limit.
Correct. It's the scientifically determined maximum safe moisture level a cargo could have before it risks turning into that dangerous liquid slurry mid-voyage. It's determined by specific lab tests.
So that's the golden rule here for the crew then. Checking and trusting that TML.
It's absolutely crucial. Masters must scrutinize the cargo declarations, the certificate stating the moisture content and the TML very closely. They have the right and duty to refuse cargo if they have doubts.
And if it happens anyway, if liquefaction is detected during a voyage.
Then immediate actions are vital. Things like minimizing ship rolling as much as possible, knowing and monitoring the ship's natural rolling period to avoid resonance with sea swells.
Like avoiding hitting the resonant frequency.
Exactly. Also, investigating any irregular rolling immediately and, crucially, planning routes to avoid heavy weather if at all possible.
And checking the cargo itself.
Yes, regular examination of the cargo surface, looking for signs of flattening, water pooling, splattering against bulkheads with photographic records is vital. The signs can be subtle at first.
Okay, so while water is a clear antagonist, the complexities don't stop there. It sounds like many dry bulk cargoes, just in their very nature, harbor their own unique, sometimes unseen threats.
They certainly do. Take ammonium nitrate-based fertilizers, ANBFs, very common cargo.
Yeah, you see that everywhere.
But these aren't just inert substances. They're oxidizing agents, meaning they can fuel fires even without air. They can self-heat, emit toxic gases, and even undergo what's called self-sustaining decomposition, or SSD.
Self-sustaining decomposition.
Yeah. And this is particularly relevant with recent amendments to the IMSBC code.
The IMSBC code, that sounds important, like the rule book.
It is the International Maritime Solid Bulk Cargoes Code. It's basically the global safety standard, the Bible, for shipping solid bulk cargoes.
And it was recently updated for these fertilizers.
Yes, these amendments aren't just bureaucratic changes. They're a direct response to some very serious incidents, highlighting the deadly realities of handling these specific fertilizers. They classify ANBFs into new schedules, like Group C and MHB Group B.
MHB.
Materials hazardous in bulk. It underscores their inherent dangers.
Okay, back to self-sustaining decomposition. That sounds incredibly serious. How do you even begin to stop that once it starts, if it's self-sustaining?
Well, that's the tricky part. Unlike most fires, SSD doesn't rely on external oxygen from the air.
So closing the hatches or using CO2 won't work.
Exactly. Smothering with CO2 or restricting ventilation is ineffective, potentially even dangerous because it traps heat and gases. The only effective response is rapid cooling, copious amounts of water. Deluge it.
What flood the hold?
Essentially, yes. Combined with opening the hatch covers carefully to prevent dangerous pressure buildup from the gases produced and to vent the toxic fumes.
Wow. That raises an important question then about preventing it in the first place. Monitoring for heat sources.
Absolutely critical. Seemingly innocuous heat sources like energized hold lights left on or nearby thermal oil heating pipes for other systems. They can potentially be enough to initiate decomposition in some types of AMBF.
So even something as simple as forgetting to switch off a light and hold could potentially have catastrophic consequences. It's quite a detail.
It really is. And there's another complication. The standard trough test used in labs to assess the SSD risk, it has limitations.
How so?
Well, a small lab sample dissipates heat much more easily than a massive pile of bulk cargo in a ship's hold.
Right, the scale is totally different.
Exactly. So the lab test might actually underestimate the real-world risk because the bulk cargo can retain heat deep inside, potentially triggering decomposition over time in a way a small sample just wouldn't show.
That highlights a systemic challenge, doesn't it?
Yeah.
How do you accurately test something at scale when your testing methods are inherently small scale?
It's a constant issue in bulk shipping safety.
Okay, sticking with fertilizers for a moment, let's talk urea. Hugely common, used everywhere, but I hear it's also highly hygroscopic, loves water.
That's absolutely right. Hygroscopic means it readily absorbs moisture directly from the air.
Like a sponge?
Pretty much. And urea's hygroscopicity, especially when the air humidity gets above its critical relative humidity, which can be surprisingly low, maybe 62.5% at 50 degrees C, conditions you might find inside a hold.
Makes it prone to
Caking, turning from free-flowing granules into solid lumps or even one big block.
Ah, another box. A urea box this time.
Could be. That's why it's common practice in many ports to suspend loading urea if the atmospheric humidity gets too high, say above 75–80% RH.
Makes sense. And anything else about urea?
Well, its low thermal conductivity is interesting. It means it acts as a good insulator.
So it can trap heat?
Potentially, yes. If there's a heat source or if it's loaded warm, it won't cool down easily.
Okay. And moving beyond the cargo's inherent properties, what about just plain physical contaminants, like loose rust, scale, or bits left over from the last cargo. This seems like a constant headache.
It is a massive area of concern. Loose scale, we mean the flaky stuff. Old rust layers breaking off, not just surface oxidation rust, can easily contaminate the new cargo.
And standards are strict.
Very. They vary by country and cargo type, but for some dry bulk cargoes, especially sensitive ones like grains or foodstuffs, holds need to be, well, the standard is often called hospital clean.
Hospital clean for a giant cargo hold.
It sounds extreme, but yes. Take the Australian Quarantine Inspection Service, AQIS. They have a notorious zero-tolerance policy for certain contaminants. Meaning even a single particle of certain previous cargoes or insects or soil found during inspection can lead to a ship failing, resulting in quarantine, costly cleaning, major delays, even denied discharge.
One particle.
It underscores the immense importance of thorough inspection and meticulous cleaning after every discharge and before every new loading. It has to be part of the routine.
So how do ships manage these incredibly complex cleaning requirements? Especially when different cargoes leave different kinds of residues, it's clearly not just a quick hose down.
Not at all. It's a highly specialized process.
No.
For really persistent residues like hardened cement, they might even need to call in professional cleaning companies.
Using chemicals.
Yes, sometimes strong acids, even hydrochloric acid in some cases, which of course requires extreme care. It's dangerous to humans and it can damage the hulled paint or steel if it's not properly diluted and handled.
And other tough cargoes.
Oh yeah. Things like coke, pet coke, certain ores. They're known for persistent staining, and that stain itself, even if the hold is technically clean, can sometimes cause a failed hold inspection, believe it or not.
So it's about specific chemicals, specialized equipment, and rigorous safety measures.
Precisely. Chemicals, if used, are usually applied with specialized gear, things like mini jets using air pressure, special foam nozzles, and robust personal protective equipment, PPE, is non-negotiable. Chemical splash suits, gloves, full face visors.
And the cleanup after the cleaning.
Critical. The operation should always finish with a thorough freshwater wash to remove all chemical traces and avoid pollution.
And the wastewater.
That wash water itself, if it contains chemicals, has to be managed according to MARPOL regulations.
MARPOL, the International Convention for the Prevention of Pollution from Ships.
Exactly. Especially if the residues or chemicals fall under Annex FAN, which covers oil, or Annex II for noxious liquid substances. You can't just pump it overboard anywhere.
And the equipment used for the actual washing, the pressure washers, they're pretty powerful, I assume. Need more than a garden hose for this.
Absolutely. High-pressure cleaners are standard. We're talking 350 to 500 bar.
500 bar, that's what, over 7,000 psi?
Around that, yeah. Serious pressure, it's often essential for proper cleaning, getting into crevices, removing stubborn residues.
Any other tech?
Hot water cleaners exist too. They're less common, maybe more expensive to run, but they can be so effective they might reduce the need for chemicals altogether in some cases.
This level of detail is amazing. From checking chemical compatibility to the exact pressure of the wash, it really shows how rigorous and scientific this whole process has to be.
It absolutely is. No shortcuts.
Okay, so we've talked ship, cargo, cleaning. But this isn't just about the vessel and its contents. It's also about the entire kind of ballet of loading and unloading, right? How do port operations play a role in preventing some of these issues?
They play a critical role. It's the main interface, really, where land meets sea.
And you've got specialized equipment.
Loads of it. Grab cranes, conveyor belts, pneumatic unloading systems. But their operation has to be meticulously managed, not just for efficiency, but to prevent product loss or damage to the ship. We talked about grab damage earlier.
Right.
Modern solutions focus on minimizing impact. Things like Cleveland Cascades loading chutes.
How do they work?
They're designed to minimize dust and cargo degradation by maintaining what's called mass flow.
Mass flow.
Yeah, essentially keeping the cargo moving as a single controlled mass rather than letting individual particles fall freely and generate dust or break apart. They often use specialized liners inside the chutes too, like UHMWPE.
UHMWPE, what's that?
It stands for ultra high molecular weight polyethylene. It's a type of super slick, incredibly durable plastic.
Ah, so the cargo slides easily.
Exactly. Dramatically reduces friction, helps prevent caking and buildup inside the loading equipment itself, keeps things flowing smoothly and gently.
So it really boils down to optimizing efficiency while prioritizing safety and increasingly environmental impact.
Exactly. Dust control, for instance, is a huge concern now. Not just because dust is lost product, but it poses respiratory risks for workers and can cause significant environmental issues around the port.
Are there tech solutions for dust?
Oh, yes. Companies like, say, Vortex Global, they offer loading solutions with inline filtration systems built right into the loading spout.
How does that work?
It actively captures any fugitive dust trying to escape during loading, collects it in filters, and then periodically pulses it back into the main load stream. Very clever. Keeps the air clean.
And the sheer volume of cargo involved.
Yeah.
It must make even a slight inefficiency multiply into huge costs or delays.
Indeed. Just think
Mhm.
about HandyMax bulk carriers.
The medium-sized ones.
Yeah, the real workhorses of the dry bulk fleet.
Hmm.
Typically carrying between, say, 40,000 to 70,000 deadweight tons.
Deadweight tons, that's the total carrying capacity.
Right. Cargo, fuel, water, crew, everything the ship can carry, moving that much material. The goal is to optimize every single step, from the mine or factory onto the train.
Speaking of trains,
Yeah, innovations even extend back into rail transport. You see things like multi-car wagon dumpers now, where whole sections of a train can be unloaded simultaneously. It further streamlines that crucial land-to-sea
it
connection.
really shows how integrated the whole logistics chain is. It's not just the ship.
Not at all. It's a massive interconnected system.
Wow. We have certainly covered a lot of ground today.
Yeah.
From the surprising design complexities hidden in a ship's hold
Mm.
to the insidious threats of water ingress, condensation, and even volatile cargo turning liquid or decomposing.
Yeah, the hidden dangers.
And then the meticulous, almost forensic science of cleaning and the tech involved in ports.
Yeah.
It's just abundantly clear that shipping dry bulk cargo is far, far from simple.
This deep dive, I think, it truly highlights that the vast quantities of raw materials and commodities underpinning our entire global economy, they rely on an incredibly precise, heavily regulated, and constantly vigilant system.
It's not just luck that things arrive.
Not at all. Every single detail, from the type of hold paint used, to the moisture content certificate for the cargo, to the way a grab is operated, it can have multi-million-dollar implications if it goes wrong.
It really is a testament to human ingenuity, isn't it? And that constant drive for safety in what is inherently a very challenging environment.
Absolutely. Constant learning, constant improvement.
So what does this all mean for you, our curious listener, tuning in?
Well, I think it means that the next time you encounter a product, any product, whether it's something in your home, your car, your workplace, just take a second to consider the immense, largely unseen journey many of its raw components probably took by sea.
That journey we just unpacked.
Exactly. And maybe perhaps ask yourself this. What other seemingly mundane processes are out there in our world, processes we take for granted, that hold such surprising depths of complexity and risk? Processes demanding constant innovation and human oversight that we rarely, if ever, stop to consider.